I'm very glad to be here. And today I'd like to talk about chiral magnetic waves in quark matter inside neutron stars and the resulting gravitational waves. And this study is based on this paper in collaboration with Naoki Yamamoto from Keio University. And this is outline of my talk. First, I'll give you some backgrounds about neutron stars and Asteroseismology. And secondly, I'll explain the chiral transport phenomenon and the chiral waves, which are basic ideas of our study. And next, we'll move on to the chiral magnetic waves in quark matter. And next, I'll show you some new type of gravitational wave, which is caused by chiral magnetic waves. And finally, I'll summarize. So let me begin with neutron stars. And as you know, stars shines by burning their nuclear fuel in them. And when nuclear fuel runs out, a supernova explosion occurs. And object left in its core occurs and finally becomes a neutron star. And the neutron stars have the following typical quantities. The mass is about solar mass, and the radius is about 10 kilometers. And the magnetic field at the surface is about 10 to 12 Fs to 10 to 15 Gauss, and temperature is about 10 to 6 to 10 to 9 Kelvin. And as you can see from mass and the radius, the neutron stars are very dense, and the typical density is about 10 to 15 gram per cubic centimeter. And in astrophysics, unraveling the internal structure of neutron stars where such a high dense environment realized is an important problem. And one way to search the inside of a neutron star is asteroseismology. So what asteroseismology is? And the term astero means stars, and the seismology is study of the earthquakes. So the frequency of the earthquakes depend on the internal structure of the Earth. So by analyzing the oscillations, we can get some information about the interior of the Earth. This is seismology. And seismic oscillations, like earthquakes, inform us about the interior of the stars. And while the starlight or electromagnetic waves such as X-rays and radio waves still remain observational probes to search stars, they carry only surface information. And on the other hand, if we can detect the seismic oscillations in some way, we can get some clues about the interior. And this is asteroseismology. And in asteroseismology, it is known that there are some oscillation modes according to their physical origins. And here, I'll give you two examples of oscillation modes. And this is a linearized Euler equation. And here, rho is a mass density, and delta means fluctuation of some quantity, and v is a fluid velocity. And p is pressure, and phi is the gravitational potential. And in the right-hand side, the first term represents the pressure, and the second term represents buoyancy. And oscillation mode, which comes from the pressure, is called pressure mode or P mode. And the P mode is like acoustic waves, and the dispersion is given by this. And omega p is angular frequency angular frequency of P mode, and Cs is the speed of sound, and K is wave number. The oscillation mode, which comes from the buoyancy, is called a gravity mode or G mode. And this is schematic figure of G mode. Gravity is acting downward, so the upper fluid layer is less dense than the lower fluid layer. And here is a fluid element, and this element oscillates like this, and this oscillation is G mode. And G mode, the dispersion relation of G mode is expressed as this, and here gamma 1 is a relativistic index. And G mode is characterized by the variation of gravitational potential, so they are called gravity mode. And Asteroseismology can be applied to neutron stars. And in the case of neutron stars, they are so dense, and so the gravitational waves caused by seismic oscillation is expected to be detected. So, and the frequency of gravitational waves is the same as that of the seismic oscillation. If we can detect the gravitational waves, we can also get some clues about interior of neutron stars. So in other words, we can see the inside of neutron stars through gravitational waves. This is asteroseismology of neutron stars. And gravitational waves are also classified as oscillation mode according to their original origins of seismic oscillation. And here we have a naive question. Are there any other oscillation mode of neutron stars? And to this question, we conclude that the chirality of quarks leads to a new type of seismic oscillation and gravitational waves. So next, I'll give you some example of chiral transport phenomenon and chiral waves, which are caused by the chirality of elementary particles. So first, let us consider the parity of transport. And electric fields induces electric currents. This is Ohm's law. And Ohm's law can be written like this. Here, E is electric charge, J is vector current, sigma is conductivity, and the capital E is electric field. And if we perform parity transformation, and vector current and electric field flip their signs, and so the signs are consistent in the both sides. So we can expect this kind of transport occur. And in the same way, we consider the magnetic field. So the question is, do magnetic fields cause electric currents? If this kind of transport happens, this can be written like this. Here, B is a magnetic field, and sigma M is a coefficient. And if we transform parity transformation, the vector current flip its sign, but the magnetic field does not, because the magnetic field is axial vector. So the signs are inconsistent in the both sides. So usually we cannot expect this kind of transport occurs. However, if the coefficient flip its sign and the parity transformation, the current can be generated. And the chiral magnetic wave effect, which I will explain in the next slide, is an example of this kind of transport. Here, I'd like to give you two examples of chiral transport phenomena, such as a chiral magnetic effect, or CME, and the chiral separation effect, or CSE. In the left figure, B is a magnetic field, and these are relativistic fermions. And spins, when spin S and momentum P are in the same direction, the chirality is right-handed. And when spins and momentum are in the opposite direction, the chirality is left-handed. And spins are aligned with magnetic field. The right-handed fermion moves in this direction, and the left-handed fermion in the opposite direction. And these right and left-handed currents are written like this. Here, mu R and mu L are right and left-handed chemical potentials. And introducing vector chemical potential mu and the color chemical potential mu5 as this, we can finally obtain the vector current, which is the sum of right and left-handed currents like this, and actual current, which is difference between the right and left-handed currents like this. The transport where the vector current is generated by the magnetic field is called color magnetic effect. And transport where the actual current is generated by the magnetic field is called color separation effect. And the color chemical potential mu5 flip its sign and the parity transformation, and this fact matches the explanation which I have explained in the previous slide. And color chemical potential is finite only when the number of right-handed fermions and left-handed fermions are different. So in other words, color magnetic effect can appear only when the system has a chirality imbalance. And also, these coefficients are related to the color anomaly, and they are quantized topologically. These are properties of color magnetic effect and color separation effect.
So can I ask, sorry, a very basic question on the previous slide?
Yes.
So the chiral, you're saying in the chiral magnetic effect, a magnetic field can induce a current because the coefficient mu5, really, mu sub 5 really, is odd under parity. Did I get that right?
Yes.
Okay, what about the chiral separation effect? Is the vector chemical potential also odd under parity?
No, vector chemical potential is even under parity, but the actual current is odd under parity.
Okay, so so I can have both of these in the same system. And so a magnetic field can induce separately right-handed and left-handed currents.
Yes.
That's what you're telling me? Okay, thank you.
Yes, thank you. And so waves which are caused by color transport phenomena are generally called color waves. And examples are color magnetic wave, color vortical wave, and color heat wave, and so on. And here I'll focus on the color magnetic wave, or CMW. And CMW is a density wave by color magnetic effect and color separation effect. Here is a magnetic field B, and if the density fluctuates, the chemical potential also fluctuates. And the chemical potential fluctuation causes actual current fluctuations because of CSE. And fluctuation of actual current induces a color chemical potential fluctuations. Again, color chemical potential fluctuation induces a vector current fluctuations due to CME, and the vector current fluctuation also induces a chemical potential fluctuation. So repeating this process, the density wave propagates along with the magnetic field. And this is a mechanism that the CMW appear. And CME, color magnetic effect, needs a chirality imbalance or finite color chemical potential to appear. But as a CMW can propagate without the chirality imbalance at the equilibrium. CMW needs only the fluctuation of the color chemical potential. And let's see how the dispersion relation of CMW is derived. We first consider the density fluctuations, and chemical potentials can be decomposed into the background and the fluctuation. And the fluctuation can be written using the susceptibility chi and the number density fluctuation. And the same goes for the current chemical potential mu5. We also need current fluctuations caused by CME and CSE. These are the CME and CSE. And using these fluctuations, the fluctuation of currents can be written like this. And finally, we combine the linearized continuity equations. And this is the continuity equation for the vector current, and this is for the actual current. And substituting these fluctuations into these linearized continuity equations, we can obtain the equation, wave equation of CMW. And this is a dispersion relation, which is derived from the wave equation. Here, K is a wave number vector. And as this shows, the dispersion relation is independent of current chemical potential. So the current magnetic wave can propagate without the chirality imbalance, as I have mentioned in the previously. And the CMW has been discussed in the context of quark-gluon plasma, which is created in heavy ion collision experiments. And however, the CMW can also appear in the quark matter of neutron stars. So from now, I'd like to talk about current magnetic waves in quark matter in neutron stars. And please note, yes?
Just remind me, it must have been on a previous slide. What is chi?
Chi, yes. Chi is a number susceptibility. So chi can be obtained by differentiate.
It's the nd mu or 1 over that or something. Okay,
yes,
thanks.
Yes. So, and please note that if I mention, when I mention quark matter, it means two flavor quark matter in this talk. So first I begin with why the current magnetic wave appear in quark matter of neutron stars. If quark matter exists in neutron stars, the quarks are relativistic because neutron stars are so dense that the Fermi surface is high. So the quarks obtain the very high energy. And as I explained, quarks, the relativistic fermions causes the Chiral transport phenomena. So, and CMW can propagate with the chirality imbalance at the equilibrium. And also, we now focus on the CMW of quark number density fluctuation. And in this case, it is not affected by the electric conductivity. I mean that if we consider the electric charge density, it is damped by the electric conductivity exponentially like this. Here, sigma is the conductivity and T is time. But in the case of number density fluctuations, there is no effect of damping by electric conductivity. And also, very strong magnetic field is expected to exist in neutron stars. And the typical field strength of magnetic field is about 10 to 18 Gauss. So above all, we can expect that CMW can appear in quark matter. And we call new type of oscillation mode, which comes from the color magnetic wave as color magnetic mode or CM mode. And this is a new kind of oscillation mode of seismic oscillation of neutron stars. And so far, I have not mentioned the quark mass effect. However, quark has a finite mass, so we need to consider the quark mass effect. And this is a quark mass term in the Lagrangian describing quarks. MQ is a quark mass, and psi L and psi R are left and right-handed quark fields. And as this shows, quark mass term appears as a mixing of left and right-handed quarks. So this means that if quark mass exists, the Chirality flipping occurs. A Chirality flipping is a phenomenon that the right-handed quarks flips into the left-handed fermions and vice versa. And this is a Feynman diagram describing the Chirality flipping by quark-quark scattering. And in the left-hand side, right-handed quark flips into the left-handed quarks. And in the right-hand side, quark does not flip quark, flip the chirality. And K prime, and P prime are the momenta of quarks, and this is gluon with a momentum transfer Q. And this scattering amplitude can be expressed like this. And ML is a longitudinal contribution, and MT is a transverse contribution. And here, J minus plus represents the currents in the left-hand side, and JH is a current in the right-hand side. And H denotes the helicity. And pi L and pi T are the longitudinal and transverse part of gluon self-energy. And we can express the possibility the Chirality flipping happens. This is the Chirality flipping rate. Here I denote the Chirality flipping rate as gamma flip. And the Chirality flipping rate is defined as this, and N5 is a chiral charge density, which is a difference between the number, this means the difference of the numbers of right and left-handed fermions. And using Boltzmann equations and these scattering amplitudes, we can obtain the Chirality flipping rate like this. The first term comes from the longitudinal contribution, and the rest three terms come from the transverse contributions. And here, alpha S is strong coupling squared over 4 pi, and mu by Q is a quark chemical potential at the equilibrium, and QD is a Debye momentum, and T is a temperature. And the first term depend on the T squared, and this matches the behavior of usual Fermi liquid, while the transverse part has a fractional power of the temperatures. This is because Landau damping. This comes from the Landau damping. However, in the case of neutron stars, the temperature is much smaller than the chemical potential. So the smaller power of temperature is more dominant. So the Chirality flipping rate comes from the longitudinal contribution mainly. And if the Chirality flipping happens, the chiral chemical potential reduces to 0. So the CMW, which is the fluctuation of chiral chemical potential, also damped by the chirality flipping. And this is a property of CMW in the quark model of neutron stars. And if seismic oscillations occurs, gravitational waves are also emitted. And in asteroseismology, the frequency and amplitude of gravitational waves is important. So here I'd like to talk about gravitational waves of the shear chiral magnetic mode. And gravitational waves are the fluctuations of space-time. So we first need to set metric. And in our case, in our setup, we set the magnetic field aligned with the z-axis. So it is useful to consider metric in cylindrical coordinates. And the metric G can be expressed the background and perturbation H. And H is corresponding to gravitational wave. And the background metric can be written like this. And here, lambda, nu, and rho are the metric functions which represent the general relativistic correction. And in general, to obtain the frequency of gravitational waves, we need to solve the linearized Euler equation. But it is hard to solve the linearized Euler equations. So in asteroseismology, the Cowling approximation is often utilized. So what Cowling approximation is? In neutron gravity, in Cowling approximation, we ignore the recoil by gravitational potential. And in the case of general relativity, we ignore the recoil by gravitational waves. This is a schematic figure representing Cowling approximation. If CMW appears as seismic oscillation in neutron stars, gravitational waves are also emitted. And the frequency of gravitational wave and seismic oscillation are the same. And here I denote it omega CM. And the stars, neutron stars, receive the recoil by gravitational wave. In the Cowling approximation, we ignore the recoil. And in this case, the frequency changes, and I denote it omega Cowling here. Then in the Cowling approximation, we assume that the frequency in the Cowling approximation is equal to the frequency of original mode. And this means that we regard the frequency of gravitational waves as the frequency of the source itself. In other words, in the Cowling approximation, to obtain the frequency of gravitational waves, all we have to do is deriving the wave equation of the source only. And this is a Cowling approximation. And these are the fundamental equations of the shear mode. And in the Cowling approximation, we set H to be 0 practically. And we also need the current fluctuations by CME and CSE. And here we also include the diffusion effect. The first terms comes from CME and CSE. And second terms come from the diffusion, and the D is the diffusion coefficient. And combining the linearized continuity equations, we can obtain the wave equation. And here we consider the general relativistic case. The original derivative changes into covariant derivative. And this represents continuity equation of vector current, and this is for the axial current. And in the case of axial current, due to the Chirality flipping, in the right-hand side, the non-trivial term appears. So combining these equations, we can obtain the wave equation of the shear mode. And finally, we obtain the dispersion relation of the shear mode in the Cowling approximation. And this dispersion relation comes from the wave equation of the source. However, in the Cowling approximation, this is also corresponding to the frequency of gravitational waves. So this represents a gravitational wave, the frequency of gravitational waves of the shear mode. And here, VCM is expressed as this. And the second term represents a damping by the Chirality flipping, which I have mentioned before. And the third term represents the damping by the diffusion. And the possible range of the frequency of the shear mode can be given like this. The lower limit is determined by the Chirality flipping because we are interested in the time scale, which is much smaller than the typical time scale of damping by the Chirality flipping. So the lower limit is characterized by the inverse of time scale of Chirality flipping or Chirality flipping rate. The upper limit is determined by the diffusion because the diffusion term includes the wave number squared. So the wave number cannot become much bigger, much larger. So the upper limit is determined by the diffusion. And diffusion coefficient is known to be rewritten using the relaxation time tau. And the relaxation time of quark matter has been calculated by them. And the result is this. The first term includes t squared, and this matches the behavior of usual Fermi liquid. The second term has a fractional power of the temperature due to the Landau damping. And in the case of neutron stars, temperature is much smaller than the typical chemical potential. So the lower power of temperature is more dominant. So here we evaluate the upper limit using the second term.
Sorry, Sota, in your
Yes.
expression for the VCM, can you remind me what those lambda and rho are? I remember they sort of appeared in your G alpha beta, but are they like over one number? Or like, is it something I can get by looking at, say, a mass or a radius of neutron stars? Where are they from? Those lambda and rho.
Oh, sorry, what number?
Is lambda and rho in your expression for V of CM?
Oh, yes. Lambda nu rho r comes from the metric functions.
And like, what if I'm given like an ordinary like neutron star of this radius and this mass? Do I know those numbers?
So typical value.
Yes, yeah.
So lambda and rho are are the correction of general relativity. So these are characterized by Gm over R.
Okay.
M is the mass of neutron star and R is the radius. And in the case of neutron stars, the typical order of magnitude is 10 to -1. So the exponential of lambda and nu are the order of 1. So they do not change the order of magnitude of the frequency.
Okay. Okay. Thank you. Sorry.
Thank you. Yeah. So, okay. So using this inequality, we can obtain the possible range of the frequency. Here we assume these values of parameters. And in this case, the range of the frequency can be written like this. And when the temperature is about 10 to 6 Kelvin and magnetic field is about 10 to 18 Gauss, the frequency is from 10 to 4 Hertz to 10 to 7 Hertz. And lower limit is lower limit depends on the t squared, while the upper limit depends on the fractional of fractional power of the t. And so when the temperature increases, the lower limit is become larger than the upper limit. So we cannot expect the shear mode can exist in high temperature environment such as supernovae. And if representing the physical parameters, if expressing the frequency with physical parameters, the frequency of shear mode can be written like this. And what is important is the frequency depends on the magnetic field inside neutron stars. So if we can detect the frequency of the shear mode, we can get some clues about the magnetic field in neutron stars. And moreover, the shear mode exists only when the neutron stars have the quark matter in them. So the existence of the shear mode itself tells us the existence of quark matter in neutron stars. So in this sense, the shear mode can be a new proof of magnetic field and quark matter in neutron stars. And we also need to evaluate amplitude, and effective amplitude of gravitational waves can be given by this formula. Here, d is a distance to the source, and g is gravity constant, and EGW is released energy as gravitational waves, and f is the frequency. And the released energy depends on events. So in a framework, we cannot determine the amplitude completely. So we express the amplitude with some parameters. And here, the energy of 10 to 44th erg is corresponding to the typical energy emitted by the giant flare. A giant flare is typical 10 to 44th erg is corresponding to 1% of the typical energy of the giant flare. And giant flare is known to be explosional event of neutron stars. And 10 kiloparsecs is corresponding to the radius of our galaxy. And so if the shear mode, the gravitational waves of the shear mode radiated by the neutron star at a distance of the 10 kiloparsecs with the energy of 10 to 44 seg, the amplitude is 10 to negative 20 seconds. And this is the amplitude of the shear mode. And finally, I will summarize.
Sorry, can I ask,
yeah.
can I, the punchline on the previous slide,
Yes.
what's the amplitude that LIGO can detect?
Okay. In 2018, the gravitational waves were detected, and the typical amplitude is 10 to minus 21. So this amplitude is smaller by tenth smaller than the amplitude of gravitational waves, which is detected by LIGO. But when we consider the possibility of the observation, we also need the frequency, and LIGO has a sensitivity around 100 hertz. So the frequency of shear mode is much larger than the frequency of sensitivity at the frequency region which LIGO can detect. So I think it's difficult to it's difficult to detect the frequency of shear mode by LIGO.
Gotcha. Thanks.
Yep.
And in his estimate, he's considering something that like a neutron star that's quite close to us, like kiloparsecs, not like the 40 megaparsecs of the neutron star merger.
Yes.
Right. Yeah.
So that's right. So if this explosional event occurs in very near position, it could be, but we also need to consider the mechanism, because the frequency is very high. So this kind of gravitational waves it needs a very short time scale event, because this kind of oscillation is excited by the for example 10 to 5th hertz. So for example, the giant flare, the typical time scale of giant flare is about 10 to 100 hertz. So we need to excite the shear mode, we need a more higher frequency event, I think. So finally, I summarize, and I showed that the chirality of elementary particles causes the chiral transport phenomena such as chiral magnetic effect and the chiral separation effect. And CMW, which is caused by CME, appears as seismic oscillations in quark matter and neutron stars. And gravitational waves are also emitted by this seismic oscillation. And this seismic oscillation and gravitational waves are the new type of oscillation mode, namely shear mode. And so the chirality microscopic quantity appears as a seismic oscillation, and the gravitational waves macroscopic quantity. So in this case, we have studied a new type of asteroseismology, namely chiral asteroseismology. And especially CM mode can be a new proof of magnetic fields and quark matter in neutron stars. And due to time constraints, I cannot explain the details, but we can also consider another type of oscillation mode caused by chiral vertical wave in the core of supernovae. A chiral vertical wave is one example of chiral waves. But in this case, Shibe mode is very strongly damped by the diffusion. So we cannot expect these kinds of modes detected. And as outlook, we need to consider contribution of magnetic fields to the Parity flipping rate and the diffusion coefficient. And in the case of Parity flipping rate, the magnetic field it is expected to that the magnetic field causes the Parity flipping rate to decreases because when the magnetic field exists, spins tend to be aligned in magnetic field, so the Parity flipping is suppressed. So in this case, the frequency, the lower limit of the frequency of CM mode can decreases, and this means that the possible range of CM mode expanded. So that's it. Thank you.
All right. Thank you very much, Sota. If there are additional questions, please speak up.
Yeah, could I ask a quick question? Thank you for the talk. So I'm just confused. Like what causes there to be an imbalance between left-handed and right-handed particles? Like what causes there to be a finite mu5? Do I excite one if I squeeze the matter, or how do I excite a finite mu5?
Okay. First, the CMW does not need a Chirality imbalance to appear because this only needs a fluctuation of chiral chemical potential or Chirality imbalance, since the dispersion relation is independent of chiral chemical potential, and this fluctuations occurs because of the fluctuation of the normal ordinal density fluctuation because of CSE. If the density fluctuates, ordinal chemical potential fluctuates, and then the actual current fluctuates. So CMW can appear only when the ordinal density fluctuation appears.
Okay, that's then I think you probably can start to talk about a bulk viscosity, which I guess is what was being talked about when I was joining. And then you well, yeah, the other thing I found interesting was, can you go to where you estimate the time scale of the restoration of the chiral imbalance?
So the time scale of Chirality flipping?
Yeah. Like you had it as a function of magnetic field. Like it was an expression where you had like magnetic field over 10 to the 18th Gauss or something.
Yes.
Do you know which, like, can you go back to that slide which had like magnetic field over 10 to the 18th Gauss so I can look at it again, please?
Here?
No, like you had an estimate for the time scale of restoring like your imbalance, and you had like part of that expression was B over 10 to the 18th Gauss in parentheses. Is that Yeah,
Here.
yeah, I guess so. Yeah, so I mean, I tend to think that 10 to the 18th Gauss is like a really high quantity for the magnetic field. Like, I would usually expect it to be much less than that. Like, I mean, at most maybe like 10 to the 16 or something typically. Like, we don't know obviously what it is, but if it were a 10 to the 16th Gauss, then your frequency would be 10 to the 5th divided by 100, which is 10 to the 3rd. So that's a kilohertz. And that's the same time scale as the density oscillation, like in a neutron star merger. So I think that's kind of interesting when it comes to talking about bulk viscosity.
Yes. Okay.
But that was just a comment, I guess.
Thank you very much.
On the last slide, you mentioned,
Yeah.
like at the very end, the very last thing you said, if I understood correctly, was that, no, the very last slide was that if you take into account the contribution of magnetic fields, I think you said that the lower frequency limit can be pushed lower because magnetic fields suppress the chiral flipping, right?
Yeah.
Does that depend on like not having a superconductor or something? My understanding is that if the quark matter forms a superconductor, then the bulk of the quark matter won't actually be permeated by magnetic fields, so I won't benefit from that. Do you know? Is that completely wrong, or have you thought about it?
I cannot accurately answer to your question, and because I do not consider the effects of Chiral superconductor. So
okay, that's fine.
But in our setup, we assume that two flavors superconductor, Chiral superconductor, because two flavors in 2SC, the Chiral symmetry is restored, so they do not obtain the mass. So in our for CMW or for Chiral transport phenomena to appear, it is crucial to that the fermions are relativistic. So if the neutrons, if fermions have the mass or gap, it can't be this kind of phenomena cannot happen. So in this sense, we consider the effect of, for example, 2SC, but so in this sense, Chirality flipping also comes from the mass effect. So if 2SC does not appear, Chirality flipping becomes much larger, I think.
Right, got it. Thanks.
Wait, what was the argument for the particles having to be relativistic for this effect to happen?
Sorry. Yeah.
Why do the particles have to be relativistic for the?
Oh, yes. So in only the case of the relativistic is essential because chirality is very defined in the case of relativistic fermions. In the non-relativistic fermions, the chirality is a not conserved quantity because we can the chirality is I mean that it's not Lorentz invariance in the case of non-relativistic case.
Yeah, okay.
Okay. I think, actually, no, I have one more question, then we can.
Yes.
Do you have candidate events for exciting? So I guess, for these to be detectable, you need quite a lot of energy to be dumped, for these to be close to detectable, we need quite a lot of energy to be dumped into the chiromagnetic wave. Do you have candidate events for accomplishing this? And do you have an estimate of like the space-time density of these events so that they might occur within our galaxy? That question.
Okay. So as I had mentioned, to excite these kinds of waves, we need not only the enough large energy, but also the time scale to excite these waves. And so the chiromagnetic wave, the frequency of chiromagnetic wave is typical frequency is about 10 to 5th to 10 to 7th hertz. So the event with a time scale of 10 to negative 7 sec is needed, for example. So I have now I do not know these kinds of events whose time scale emitting energy is too close to 10 to negative 5 sec. I do not know these kinds of events, but I think, for example, chiral plasma instability, which is a mechanism of very strong magnetic fields created by the chiral transport phenomena. And in the case of chiral plasma instability, it might excite these kinds of oscillations.
Gotcha. Thanks.